Welcome to Calculus. Today we'll investigate evaluating integrals using the fundamental theorem of Calculus 1, and we'll take a look at two piecewise functions. Our first integration is from -5 to 0 of the function x plus the absolute value of 3x plus 6 dx. Now I want to treat this function really as a sum. I want to share this function with two integrals. So my first step is going to be to split the integral into two. So I'm going to redefine this as equal to the integral from -5 to 0 of x, the linear parent, dx, plus the integration from -5 to 0 of absolute value of 3x plus 6. Once I make that new sum of two integrals, I also want to consider this second one really again as 2. I need to think about the graph of that absolute value of 3x plus 6. So just kind of picturing it as a rough sketch here. That's going to be an absolute value function with its vertex on the x-axis. So I want to locate where that vertex is, and then I'm going to define that as two linear functions. But let's take a look at the graph of that absolute value of 3x plus 6. So to locate the vertex, I'm just going to set that equal to 0 without the absolute value and then solve. So I'll move the 6 by subtraction. 3x equals -6. And by division by 3, x equals -2. So that means that the vertex for this absolute function is here on -2. Well, one of these sides is going to be positive slope of 3 and pass through the y-axis at 6. So a pretty steep. And then on the left side of that vertex at -2, 0, because of the absolute value, this side that would have continued below the x-axis has been reflected up. So the way I'm going to define this absolute value is really as two separate linear functions. So from, in fact, let's write it here. We're going to define absolute value of 3x plus 6 as a piecewise function with a linear function -3x plus 6. And we'll say that that's in effect when x is less than -2. On the right side of that vertex, it's going to be the positive version, 3x plus 6. And again, that's going to be when x is greater than or equal to -2. So I want to split this integral into two more parts. So I'll keep that first integration from -5 to 0 of x dx. But then I'm going to split this absolute value portion of the integral into two. And I also have to split the domain, and the cutoff here is at -2. So I'm going to evaluate from -5 to -2 for that first version, the negative one. So that's going to be -3x plus 6 dx. And then from -2 to my upper limit of integration at 0 of the positive version, +3x plus 6 dx. And now I can integrate these three separately as usual as definite integrals. So for this first one, the linear parent, that's going to be the integral or the antiderivative 1/2 x squared. And we're going to evaluate that from -5 to 0. For the first version of my linear function, the left half of the absolute value, I'm going to evaluate that from -2 to -5. So this is, I can think of this as -3x minus 6 if I distribute that negative. So for the first one, it's going to be -3 times 1/2. This is the antiderivative, x squared, minus 6x And again, that's going to evaluate from -5 to 2, -2. And then for my last integral, that's going to look a lot like my second one, just positive instead of negative. So it's going to be 3 times half times x squared plus, on this version, 6x. And according to its limits of integration, it's going to integrate from -2 to 0. So now we're ready to evaluate a lot of algebra at this point. So according to the fundamental theorem, I can evaluate this by plugging in 0 to the function and then subtracting from it the function evaluated at -5. So this is going to become half times 0 squared minus half times -5 squared. Then we'll do the same setup for my second integration. So there I'm evaluating from -2 to -5 for the reverse order. So I'm going to combine these two multipliers. -3 times half is going to be -3 halves. So I'm going to write plus, put my brackets, and then I got -3 halves. What we'll do is substitute in -2 first, my upper limit of integration squared. I'm going to put extra parentheses here, -6 times -2. And we're going to subtract from that the same function evaluated at -5. So -3 halves times -5 squared minus 6 times -5. And we'll go ahead and set up that third integration. Again, it will look very similar to what we just integrated, but the positive version. So now we'll have, again, 3 halves, but this is now positive. This version's being integrated from -2 to 0, so my first limit of integration is going to be 0, so 0 squared minus 6 times 0. And then evaluated at -2. So 3 halves, positive 3 halves, times -2 squared, minus 6 times -2. So a lot of simplification that we need to do. We can note a few cancellations because of 0 multipliers. So this first term is going to go. In fact, this whole interior piece is going to go as well. Again, those are canceling because I've got 0 multipliers. Now I want to evaluate what I do have that's not going to reduce to 0. So for this first multiplication, I got -5 being squared, so that'll become positive 25. Half of that is 12.5, but then it's multiplied by a negative. So the ultimate outcome of this first integration is going to be -12.5. Now we'll consider that second one, the negative version. So right here I've got -1.5, or -3 halves times -2 squared. So that's 4 divided by 2 is 2 times -3 is -6. And then, so again, that's this part here. Let me not get ahead of myself. That's this part. And then subtracted by 6 times -2. So that's going to turn positive. So plus 12. So the ultimate outcome there is going to be -6. So it's good to do these in parts, just to kind of make sure that the arithmetic is accurate. So for this second one, we're subtracting. Here I've got -3 halves times -5 squared. So that's 25. Half of 25 again is 12.5. And times -3, 12.5 times -3 is going to be -37.5. And then -6 times -5 is plus 30. So what's coming out of this addition is negative 7.5. Negative 37.5 plus 30 is negative 7.5. And that's going to end up ultimately adding to my 6. I think I've made an error with the sign on that 6. That's going to be positive. So we'll come back and we'll combine these parts, but we're just putting our thumb there. There's one group of calculations left to simplify. So that's this last expression here. So it's negative out front, and then 3/2 times negative 2 squared. So that's 4. Negative 2 squared is 4, divided by 2 is 2, times 3 is 6. And then negative 6 times negative 2 is going to be 12. So 6 plus 12 and that's ready for us to bring over to, I see I've got another sign error here. This should be plus. Again, I'm picking that up there. So what I've got here is going to be minus. So it's important to mind the signs with this, especially as we round the bend to finalize the calculation. So I'm going to grab our parts that we calculated in pieces. So I got negative 12.5 plus, I'll put it in parentheses, positive 6 plus 7.5. And then minus 6 minus 12. So that's minus negative 6. And adding that all together, we're going to get negative 12.5 plus 13.5 plus 6. And the ultimate outcome of negative 12.5 plus 13.5 is 1. 1 plus 6 is 7. 7. And since we're referring to an area, that's 7 square units. All right, so that's an example where I have an absolute value function and I split it into two linear functions in a piecewise arrangement. Let's take a look at one second example that involves a piecewise function that's already defined for us. So here I want to integrate from negative 2 to 1 of f of x dx, and f of x is defined as 2x plus 1 when x is less than or equal to negative 1, and then changes over to negative 2x minus 3 when x is greater than negative 1. So I'm going to use a similar strategy where I just split this integral into two and integrate each of these pieces separately. So we're going to start the integration at negative 2, but we're going to stop it at this cutoff point that's defined in the piecewise function as the trade-off from one part to the next. So that's at negative 1. And so when x is less than negative 1, the function is defined by 2x plus 1. So that's what I'm going to integrate from negative 2 to negative 1 dx. And then plus the integration will pick up at negative 1 and integrate to the upper limit of integration, positive 1. And that's going to be the second function. So when x is greater than negative 1, the piecewise function is defined by negative 2x minus 3. So just like with our previous example, once I have it set up, I can do the definite integration as usual. So this first function is going to become 2 times 1/2, this is the antiderivative, times x squared plus 1 times x. And that we're going to integrate from negative 2 to negative 1. Plus, so again, I'll integrate this second version, it'll look very similar. It's also linear, so -2 times, here's the definite, or the antiderivative, half times x squared minus 3 times x. And this is integrated from -1 to 1. So I can clean this up and start running the evaluation. So 2 times half is going to reduce to 1. So this is essentially x squared plus x. So as I set this up, I'm going to substitute in -2 first. So -2 squared plus -2 minus, and I see that I've flipped my order. I need to put the upper limit of integration first. So -1 should go there where I had -2's. The -2's will go in the second version. So -2 squared plus -2. Now we got the right order. And then pick up with our second integral. Plus, so here I also have a cancellation. That's going to become -x squared minus 3x. So I'm going to evaluate negative. Here my upper limit is 1 squared minus 3 times 1 minus my lower limit is going to be -1. So I'm going to plug in minus -1 squared minus 3 times -1. So that sets up the expressions that I need to evaluate to complete the integration. So we just need to treat these in parts. So -1 squared is +1, -1's 0. That whole first term becomes 0. Minus, so here I've got -2 squared, that's 4, plus -2's 2, so -2. And then I'll pick up with my second integral plus, so this is +1 squared is 1, so -1 minus 3 is -4. Minus, and then -1 squared is 1, -1 plus 3. -1 plus 3 is going to be 2. So what I've got here is -2 plus -4 minus 2. And that's all going to add up to -8 square units. And that completes our second example. Well, thank you for joining for these two examples investigating finding the integrals of piecewise functions using the fundamental theorem of Calculus 1. See you soon.